Welcome to today's lecture. We will continue our discussion on the analysis of fluid inclusions and the data that we get from them and how we could augment the data that is generated by fluid inclusion microthermometry with the data that is generated by instrumental analysis through our destructive or non-destructive methods. To continue what we were discussing in the last class about the results of ion chromatography, in which we the result that we obtain by ion chromatography is the analysis of different anionic and cationic species in concentration units of ppm or ppb, and then knowing the leachate volume and also having a good idea about the volume of the inclusion fluid that could have been liberated in the process of cross leaching. We convert the concentrations from leachate to the concentration in the inclusion fluid, and here is one more a little bit of an example that these kind of these inclusions are understandably have been studied by microthermometric methods in depression of freezing point, and we have the weight percent NaCl equivalent, and we have measured the concentration of this species as potassium, sodium, calcium, and we could have such kind of formula that the total NaCl that we got. So, from the total dissolved solid in terms of NaCl equivalent, this that we suspect that there are other cationic species, and the so now if we see that this analysis satisfies the charge balance, and then we invariably it will not, but then it has to be within the permissible limit, and we can also get some idea about what could be the total NaCl that could be present, which would be as a total coming out from the molality of the NaCl and the molality of the NaCl into potassium by sodium, because this is exactly because they are monovalent 1:1 electrolyte, and if we have calcium chloride, magnesium chloride, then that is actually contributing to 1.5 m NaCl. So, the total NaCl that we would have got. So, now from this we can always, so this we have got from the freezing point depression, and this we can the ratios we know, this potassium by sodium and the calcium by sodium or magnesium by sodium, or for that matter even if we have analyzed some iron, and then can calculate what is the actual NaCl that is present and also the other species that are present, and to do any kind of analysis or any other kind of exercise that we want to do with this characteristics of the fluid, to understand alteration characteristics and to understand their spatial variability and so on. So, this is all about the cross leach method and the analysis by ion chromatography, and just about a brief idea as to how we use them. So, this cross leach, the leachate that we obtain in a cross leach method can also be analyzed by an inductively coupled plasma, either it could be an atomic emission spectrometry or an optical emission spectrometry or a mass spectrometry. We will not be discussing about these, they simply work on the principle of the concentration versus the intensity of the emission or the optical in the optical range when the ions are emitting wavelength, characteristic wavelength after they are excited. So, the analysis this inductively coupled plasma mass spectrometry analysis is a improved technique in which we can analyze to much lower concentration in going to even parts, sometimes even a few parts per billion, or going to even parts per trillion sometimes if we have well characterized, well calibrated the instrument. It also works on the as a quantitative method, it also works on reference standards, well calibrated reference standards with concentration ranges, and here the analyte, that is our leachate, is injected into a nebulizer where it is converted into an aerosol, and now it is introduced into a plasma which is created by in a gas in an environment of argon by raising the temperature to almost 7000 to 10,000 Kelvin, and by combination of the proper radio frequency that you can generate in the instrument. And the whole idea is that the analytes are converted into their ionic state and mostly singly positive charged ions, and in that particular temperature, the degree of ionization is quite substantial. We can expect that a large part of the analyte would be in an atomic in an ionic state. Now, once they are converted into an ionic state, they could be guided through some ion focusing by appropriate application of the current in the which essentially are called the ion lenses, but only just a combination of the current that is applied, so that the ions are focused and are guided through a quadrupole, where there are 4 rods which are having oppositely charged oppositely with provided with direct current voltage and radio frequency voltage, and they are taken to the detector, where the detector could be a device in which the ions hitting the detector and the signal that will be generated is proportional to the concentration of the ion. So, this particular method is definitely it is far more involved or complicated than a normal ion chromatograph, but here also we get concentration range in terms of ppb, ppt, as we expect very low concentrations in the inclusion fluids, as we discussed. So, trace concentrations of the lighter elements or even elements like rubidium, cesium, or these base metals like copper, lead, zinc, gold and iron, etc., could be analyzed with such kind of method. So, this is also that was the destructive method in which we are analyzing the aqueous liquid for its concentration of different aqueous species. So, the other type of species that we have in the fluid inclusions are the volatiles. They are the carbon dioxide, methane, the sulphurous vapor and so on, H2S or SO2. So, how we generally could analyze them? So, for that we definitely have to release the volatile species, the gaseous species from the inclusion cavities, and that we can achieve by heating to a high temperature. This could be achieved by designing some kind of a chamber in which the kind of a furnace where the temperature could be raised to very high values, 1000 degrees or even more than that, in which we could ensure that most of the inclusions which had these volatile species like carbon dioxide, methane, or the other species like H2S and argon, nitrogen and so on, could be released from the sample. And now, if we if this is a chamber in which we have heated, we have produced we have supplied heat to this particular chamber, and here the sample which we had with containing inclusions, which we have done the petrography and have reduced them to a workable size, so that the decrypitation will be more efficiently achieved there. And if we can carry this, or whatever volatile is released within this particular chamber can be carried with a carrier gas, and this carrier gas along with the gases which is liberated from this particular decrypitation process can be taken to a gas chromatography to analyze the different gases. And such kind of analysis are also also standard based. If we have some standard materials in which the concentration of these gases are in known quantity, then we can always get a quantitative estimate, or just by getting the if we don't, you can also do it by a qualitative analysis. So, the principle of the gas chromatography is more or less similar to the ion chromatography that we discussed before. It also has a mobile phase to which the gases get attached, occluded, adsorbed in some mechanism, and then the gas which is flown through, it also acts as something like a similar in the mechanism to the element there, and different gases are released at different time from the stationary phase, and they could be seen on a chromatogram where the peaks will be there for different gases, say gas 1, gas 2 and gaseous species 1, 2 and 3 and so on. And the positions of this kind of or the sequence in which in a mixture of these gases, which gases are clearly sequentially released is known, and then from that at least we could make a qualitative estimate about the gases that are present in these inclusions. The other aspect or the third component of the fluid inclusions are the daughter crystals. Daughter crystals are usually, in many of the cases, are identifiable. It is the major important, one of the important objective is to actually identify the daughter crystal which is inside the inclusion cavity. Sometimes a daughter crystal like halite is possibly could be easily identified, and but sometimes there are daughter crystals which also remain unidentified in some situations where there are multiple daughter crystals which occur in situations like a porphyry copper deposit or many such. Even sometimes there are many different types of daughter phases which are observed in inclusion cavity. So, one of the ways to identify and also to have kind of semi quantitative information about the daughter crystal is to study them in a scanning electron microscope. So, as we know that scanning electron microscope is essentially is a method which gives the characteristic on the surface features, surface characteristic just to maybe just about few nanometer deep. So, it is always that inclusions or the samples which contain the daughter crystals can be, when they are polished for a preparation of a normal wafer or the doubly polished thin plate in which we study the fluid inclusions, it is also quite probable that the inclusion cavities would have been opened, and the inclusion cavities, when they are opened, the daughter crystals generally remain in them adhered to the wall of the inclusion, the cavity, inclusion cavity, and when we see them under in a scanning electron microscope in a very high magnification, we see very conspicuous and very clear picture, 3-dimensional image of the daughter crystals, because the liquid part of the inclusion has been drained out, has been opened and leaked out. It is only the solid part which are remaining. So, these images have been taken from standard literature which are available to just give you an idea about how they look like, and there are several such many such illustrations in literature which are available, one can find them out. So, here in this case there is one halite, sodium chloride, sylvite and an anhydrite, these three solid crystal phases within an inclusion cavity which is shown here in quartz. This shows a inclusion cavity, there is iron chloride Fc and something like a Salton C items named under the geothermal system Salton C, which is sodium, potassium, magnesium, iron chloride, and this is a inclusion which is ferropyrosmalite, which is iron, silicon, oxygen, chlorine species, and this is a siderite, and sometimes there are many phases which we can identify or can label them as unidentified phase. So, other than just getting the, and these also help us because you can see the crystal morphology very clearly. For example, we see a cubic crystal, we can identify that as a halite, or we see a prismatic crystal like this which can be suspected to be a sulphate like an anhydrite or a gypsum. Now, they can still further be forward, the procedure can still be improved, because if we can if we have an energy dispersive analysis attachment, which is basically known as the EDX. So, that give qualitative picture, qualitative idea about the composition of the solid phase. That becomes even further easier to identify or exactly know to what the mix. There could be in terms of the elemental like sodium, potassium, calcium or iron or chlorine. So, these peaks will be obtained when we use an energy dispersive X-ray in a scanning electron microscope. Sometimes it is also there is also report that such kind of samples could also be amenable to some X-ray diffractometry kind of study, in which if the daughter crystals present in the inclusions can also have can be also be identified from their peaks on the X-ray diffractogram. So, this is just a little bit of idea as to what we can do to these inclusions. So, this is also a destructive, this can also be called as a destructive, in a way destructive method, because we are not able to utilize this particular inclusions again, but the wafer in which we are studying could possibly be again studied. But as far as the inclusions are concerned, we have opened them up. So, they could also be coming under the destructive method. Well, so this this much of brief idea about the destructive methods of analysis of fluid inclusions. We will now move over to a discussion on the in situ non-destructive analysis of inclusions. So, here it is in situ means we know that the wafer or the fluid inclusion section that we have used for doing our routine petrography, and also have taken the chips for microthermometry. Such kind of chip can be used in this analysis without actually destroying the inclusions. And one such very popularly used instrumental methods is Raman microspectrometry, in which we use the of course very proudly use this concept of Raman scattering, which is essentially a manifestation of the molecular species depending because of the covalent bonds that the atoms are combined with, and the vibration ranges the molecular within the infrared range of vibration for these molecules. That principle is utilizing the principles of interaction of electromagnetic radiation with the bonds in the compounds. This phenomena is very effectively utilized in studying the or characterizing substances, and there also can be very widely used for characterizing contents of inclusion fluids from all types of environments representing all the spectrum of processes that we have discussed. We have also at times have referred to this particular technique before for analysis of or detecting the presence of methane and so on. So, it is essentially a micro technique. So, it has to be a device, so which will be essentially the Raman spectrometer. We need to, for this is for a specialized for purpose of fluid inclusion analysis, or for any other geological application, it has to be mounted on microscope, and some such devices are quite available now in many established laboratories, where routine Raman microspectrometry is being done to characterize fluid inclusions. And since, as I told, that this will also be an instrumental method which will be within the jurisdiction or within the purview of a person who is doing the fluid inclusion work, because it is it does not require a very specialized person to run the equipment. A person or it's rather it is more advisable that a fluid inclusionist also has the necessary idea about the working principles of the Raman spectrometry, Raman microspectrometry, because it is the material that is actually known to him only or her, and the choice of inclusion, or exactly because since these are done under the microscope, so the individual inclusion, so the it's actually is an analytical procedure which is taken on individual inclusions. So one has to know very well, identify the particular inclusion under the microscope and the inclusion to be analyzed. So it requires the that the person who does the fluid inclusion work is actually doing the analysis of the inclusions that he studies in his own samples. So I will just quickly browse through the underlying principles, the basic principles, governing principles of Raman spectrometry. So as we have said that we are essentially dealing with molecular vibration of the bonds which make the molecules, our familiar molecules, water, carbon dioxide, methane and many other molecules. And if we see the entire range of the electromagnetic spectrum starting from radio frequency, which are applicable to our study nuclear spin resonance, to as small electromagnetic radiation in the wavelength is the gamma rays, and the range of the wavelength in which the interaction this interaction process or scattering process is studied is this particular wavelength corresponding to IR, because that is the wavelength which or the frequency which corresponds to the vibration of the bonds which binds the molecules. And so here is the range. So Raman scattering, as we all know, that it is inelastic scattering, means the interaction of the electromagnetic energy with the molecule, the bond of the molecules happens in such a way that the incoming or the incident electromagnetic energy either loses or gains in energy, in contrast to a perfectly elastic scattering in which the incident electromagnetic energy neither loses nor gains in its energy and emits in the same wavelength and frequency. But the problem is that it is a weak scattering, and we can all think of that if the quantum of electromagnetic energy which is undergoing inelastic scattering will be something like 10 to the power of minus 6 part of the intensity of the electromagnetic energy which actually undergoes inelastic scattering. So normally in that case to study this inelastic scattering would be very difficult to do it with ordinary light, in the the common light, the ordinary light that we are using. So we need to have electromagnetic energy or the light which will of a much higher power than the normal light that we generate by a normal device. So it has to be a laser, that is a light amplified by stimulated emission of radiation, and these kind of lasers are generated by many different devices. They could be, and also the materials. The kind of laser that we use for my laser Raman microspectrometric study are generally low power laser, and they could be the gas laser like argon ion laser, or maybe solid state laser, which will be having the power of 20 to 100 milliwatt range of power. And since for geological applications these kind of ranges are sufficient, and that is why the methodology actually is very popularly known as the laser Raman microspectrometry, or LRM. And so the fundamental aspect is that it is inelastic scattering, and it results out of the interaction of the electromagnetic energy with the bonds, vibrating bonds in the molecules. So if we can understand them by using quantum theory, which will be a bit difficult for us to understand, and also it will be a bit out of scope of this particular lecture series, but Just to begin with, that we know that interaction of a photon, the photon will be having the energy of h nu with a vibrating molecule. So, elastic is no change in frequency, inelastic is the incident photon loses its energy by a quantity delta E, and the emitted scattered photon is frequency changes from nu minus delta E by h, means it will be emitted with a frequency which is less than the original incident frequency by a quantity which will be the difference in energy divided by the Planck's constant. Or it may happen that the incident photon gains some energy. So, it will all be depending on the vibrational state, that ground state or excited state between the bond of the molecule and the incident electromagnetic energy. So, the thing is that the vibrate, so but as you will see in the subsequent slide, these molecules which are the atoms are bound with these bonds are joined or connected through the bonds. These bonds are actually vibrating, and there will be many vibrating bonds and many such vibrations that is possible in a particular molecule, but all the vibrations will not be resulting in inelastic scattering. So, that is actually governed by some principle which is known as the selection rule as per the quantum theory, but we will rather take a easier route to understand it by the classical concept. So, here it is shown here that think of a molecule in which these atoms are the M1 and M2, and the bond representing the bond actually which joins the two can be thought of as a spring which is having a spring constant, and this frequency of the vibration of the molecule will be a simple formula, this force constant divided by the Mr, which is basically M1 into M2 by M1 plus M2. So, here that means from this, for many given any particular bond this force constant value and the mass of the atoms, we can always calculate or know what are the different frequencies in which the bonds will be vibrating. Here is a very crude and rather schematic representation of what exactly happens. So, this is the incident, this represents our molecule in which the atoms are joined or connected to this bond. The bond is like a spring which is having its own vibration as per the formula that we have given here. So, now if this is the incident electromagnetic energy and it interacts with this bond, then what will actually happen? So, this black line represents the incident electromagnetic, the frequency, and the wavelength representing the incident electromagnetic energy, and which is also shown as the same black wave which is going, which is getting reflected or scattered, retaining its frequency and the wavelength exactly. And as we said that this is the major part of it, this part is the major part which is actually scattered. Now, this green is representing the emitted electromagnetic energy with the frequency which is nu minus delta E by h, and this red in which we see that the frequency is increased is actually emitted as nu plus delta E by h. So, actually it is actually they are travelling the same distance and same, it is just only a representation just to distinguish them. So, this is the so this is the a kind of a schematic representation of what happens to explain the process. So, this wave represented by green and the blue, they represent the inelastic part, and the one which is black is the elastic. So, the black is elastic and the green and the red are inelastic. Okay, now we take the little bit of an easier route to understand the situation here, what exactly happens in a elastic and inelastic scattering. These have been taken from standard textbooks like the Introduction to Fundamentals of Molecular Spectroscopy by Manuel and McCass, and any interested reader who wants to know a little more about it or have a better more fundamental idea about the spectroscopy as it is applied. So, both infrared and Raman spectroscopy are covered as a part of molecular, they are the molecular spectroscopy. So, quickly browsing through the principles. So, whenever there is an electromagnetic energy, electromagnetic wave is interacting with a molecule. So, actually what happens is the electric field of the electromagnetic energy which is responsible in inducing a dipole in the molecule. So, molecules have got their inherent dipole moment. For example, a water which has a higher dipole moment than carbon dioxide, but inherent dipole whatever it could be, but this incident electromagnetic energy, the electrical field of that part induces a dipole, it induces a dipole, and which is this mu is the size of the induced dipole, which is proportional to the applied electric field of the electromagnetic radiation, and the proportionally constant is alpha, it is the polarizability of the molecule. So, this is a very important parameter in relation to Raman spectroscopy. So, if a sample is subjected to beam of radiation of frequency nu, the electric field experienced by each molecule is actually given by. So, the electric field E is the E 0 plus sine 2 pi nu t. So, nu is the frequency, and alpha is given by this formula, that alpha 0 into beta sine 2 pi nu vibration into t. So, if we replace this alpha in the expression of the induced dipole, that is mu, then we get an expression where it is alpha E 0 sine 2 pi nu t, and if we expand it just by using our trigonometric relationship in case of this sine 2 theta kind of expression, then we get a component which is alpha 0 E 0 sine 2 pi nu t plus half of these terms which is coming into here is first term where it is, you could see that nu minus nu vibration into t, and here it is nu plus nu vibration into t. So, here we see that the incident electromagnetic, and so this part is representing the scattering, a Rayleigh scattering, which actually is not involving any loss or gain of energy, and the light the energy is emitted by the same frequency nu, whereas the other situations which is possible here is that here it is actually going by a emitting by a reduced frequency, and here it is an added one. So, this components, one is the where it is actually the part, this inelastic scattering is actually two different types of possibilities which can happen. One is a loss in the energy or the frequency, and the other one is gain. So, the first one is basically known as the Stokes scattering, and the other one is called as the anti-Stokes scattering. So, here alpha 0 is the equilibrium polarizability, and the beta is the rate of change of polarizability with the vibration. So, this is a pictorial presentation as to what happens. So, suppose we have a molecule of hydrogen in which the bond direction is in this shown on the paper, perpendicular to the paper, and the direction of the electric field is shown by the arrow in one case, and the other case it is the direction which is shown parallel. So, here the intensity of the induced dipole moment is different in different directions of the bond axis with respect to the direction of the applied electric field. In case of B, it is higher, where the direction of the electric field is parallel to the direction of the bond axis, and is lower in case of the case where it is perpendicular. And now we come to, because we deal with the normal, our inclusions contain the gas molecules, water, carbon dioxide, and let us see, let us try to look through this procedure by very simple consideration. And this is the water molecule. So, we have now know the background that depending on the electric field and its interaction, the polarizability is something which is coming out to be a very important parameter as far as the scattering is concerned. And now let us see this water molecule, which can be visualized as a molecule which is nonlinear and is bonded in this way with the 2 hydrogen atom and 1 oxygen, the stronger O and H bond with the weaker H and H bond, which is conventionally represented, you can see in any textbook. So, this molecule of water can have 3 such different states, where the arrows marked is essentially that there is force acting on it, so that these bonds are actually stretched. All the 3 bonds are in a state of stretch. This can be called as one mode, which I will come to later. And this is one possibility, that this bond, which is the HH bond, is undergoing a bit of bending, and the OH bonds are stretched. In this case, it is the OH bond that is getting bent and the 2 other bonds are getting stretched. So, these are the 3 possible states in which the molecule of water and the bonds of hydrogen and O and H bonds would be in a state of vibration. So, when we look at any molecule like this, we think of, or we know that what we can call as something as a normal vibrational mode. So, a normal vibrational mode is one in which all the atoms vibrate in the same frequency and move in phase, even though their amplitudes could be different. Now, there is a simple thumb rule which is adopted here, that if the molecule is non-linear, so this we will call as a normal mode. There are vibrational modes, fundamental modes, and which we call this in particular as the normal modes, which are essentially important for Raman scattering, to understand the Raman scattering. And this is the thumb rule, that the number of such normal modes, normal vibrational modes, will be 3n minus 6 in case of nonlinear molecules. So, n stands for the number of atoms. So, if we have a atom of water in which there are 3 atoms, sorry, a molecule of water in which there are 3 atoms. So, 3 into 3 9, 9 minus 6. So, there are 3 fundamental or normal vibrational modes, which are shown with this nu 1 as 3625 centimeter inverse, nu 2 as 1595 centimeter inverse, and nu 3 as 3756 centimeter inverse. And now, we said that the Raman scattering is actually the Raman scattering would be involving interaction or inelastic scattering of the incident electromagnetic energy with the bonds of the molecule. Now, if there are 3 fundamental modes, vibrational modes, then will the scattering or Raman scattering take place in all the 3 modes, or it will be observable in only one or more or less than the total number of vibrational mode, and if so, why? So, we will continue discussing on this in the next class. Thank you.